Distributed algorithmic mechanism design. Most discussions of algorithmic mechanism design (AMD) presume the existence of a trusted center that implements the required economic mechanisms. This chapter focuses on mechanism design problems that are inherently distributed, i.e., those in which such a trusted center cannot be used. Such problems require that the AMD paradigm be generalized to distributed algorithmic mechanism design (DAMD). We begin this chapter by exploring the reasons that DAMD is needed and why it requires different notions of economic equilibrium and computational complexity than centralized AMD. We then consider two DAMD problems, namely distributed VCG computation and multicast cost sharing, that illustrate the concepts of ex-post Nash equilibrium and network complexity, respectively. The archetypal example of a DAMD challenge is inter-domain routing, which we treat in detail. We show that under certain realistic and general assumptions, one can achieve incentive compatibility in a collusion-proof ex-post Nash equilibrium without payments, simply by executing the border gateway protocol (BGP), which is the standard for interdomain routing in today's Internet. Introduction. To motivate the material in this chapter, we begin with a review of why game theory is relevant to computer science. As noted in the preface to this book, computer science has traditionally assumed the existence of a central planner who dictates the algorithms used by computational nodes. While most nodes are assumed to be obedient, some nodes may malfunction or be subverted by attackers. Such Byzantine nodes may act arbitrarily. This book's founding premise, in fact, is raising the entry, is that there are many computational contexts in which there is no central or cooperative authority that controls the computational nodes. In particular, the Internet has changed computation from a large local endeavor to one that frequently involves diverse collections of individuals or machines acting on their behalf. For example, web services, peer-to-peer systems, and even the interaction among packets on a wire are all cases in which individuals with no ties to each other except perhaps a common interest in a document or simultaneous use of a link find themselves interacting over the Internet. In such cases, it is often best to treat the computational entities as independent and selfish agents, interested only in optimizing their own outcome. As a category of behavior, selfishness lies between the extremes of automatic obedience and Byzantine disruption. Self-agents are unwilling to follow a central planner's instructions, but they do not act arbitrarily. Instead, their actions are driven by incentives, i.e., the prospect of good or bad outcomes. The field of mechanism design, described in Chapter 9, has shown how, by carefully constructing economic mechanisms to provide the proper incentives, one can use selfish behavior to guide the system toward a socially desirable outcome. This book is devoted to exploring the interaction of incentives and computing, a topic that has come to be known as algorithmic mechanism design (AMD). Substituting a decentralized set of incentives for a central planner is a radical departure from traditional algorithm design. However, most work in this new field of AMD assumes the presence of a central computational facility that performs the calculations required by the economic mechanism. In auctions, for example, the agents each have independent goals and desires, but the computation to determine winners and payments is done by the auctioneer, and the hardness of the computation is evaluated using traditional notions of complexity. See, for example, chapters 1, 9, 11 and 12. As such, AMD considers novel incentive-related algorithm design, but uses a standard centralized model of algorithm execution. This combination of decentralized incentives but centralized computation applies in a wide variety of settings, many of which have been described elsewhere in this book. This approach requires transmitting all the relevant information to a single trusted entity, hereafter called the trusted center, which is feasible if one such a trusted center exists. And 2. The communication required to transmit the information and the resulting computational burden on the trusted center are both manageable. However, if either of these two assumptions fails, then a more decentralized approach must be considered. As we discuss in more detail in section 14.3 of this chapter, the problem of interdomain routing is one in which a decentralized approach is valuable. The Internet is a collection of smaller networks called autonomous systems, ASICs, that are stitched together by the interdomain routing system to form the fully connected Internet. The interdomain routing system therefore plays a crucial role in the functioning, even the existence, of the Internet. However, any approach to interdomain routing must address the challenges of trust, scalability, and reliability. The ACEs are competing economic entities who want to optimize the routing outcome achieved and minimized the private information revealed. Accordingly, they not only act selfishly, but are also unwilling to share private information with or cede control to any trusted center. Thus, the ACEs must distribute the route computation among themselves. Even if trust were not an issue, scalability would drive the system toward distributed route computation. Centralizing the route computation would involve transmitting the entire AS graph to a central location and updating it whenever the graph changed. Given the considerable size and volatility of the ACE graph, such a centralized route computation would be infeasible. Similarly, the need for reliability, so crucial in the Internet, tends to favor decentralized designs. In a centralized design, the trusted center becomes a single point of failure. The fate of the entire network rests on the single system that could fail or be subverted. As an example of how scalability and reliability can drive the need for decentralization, we note that current intra-domain routing algorithms, which do not span more than one AS, and so are designed with the assumption of a mutual trust among routers, are almost all distributed. Thus, there is a need to decentralize not only incentives but also computation. This leads to distributed algorithmic mechanism design (DAMD), which is the central focus of this chapter. DAMD has the same dual concerns, incentive compatibility and computational complexity, as AMD, but it differs in two important respects. The first difference involves the nature of complexity. DAMD's measure of computational complexity is quite different from AMD's because the computation is distributed. Any measure of the complexity of a distributed algorithm executed over an interconnection network T must consider at least 5 quantities: the total number of messages sent over T, the maximum number of messages sent over any one link in T, the maximum size of a message, the local computational burden at each node, and the storage required at each node. If a distributed algorithm requires an excessive expenditure of any one of these resources, then its complexity is unacceptable. We will use the term network complexity to refer to these and other metrics of the difficulty of a distributed implementation. if the domain interconnection network T is trusted by all the agents and can feasibly serve as the trusted center, then the measure of complexity is the main difference between AMD and DMD. However, if the distributed computation is done by the agents, then a second difference arises: the strategic nature of the computation itself. In AMD, agents can manipulate a game only by their selection of actions among those described in the definition of the economic mechanism. They cannot affect the computation of the mechanism because all outcomes are computed by the trusted center from the vector of strategies according to the definition of the mechanism. If the agents themselves perform the computation using some distributed algorithm, then they have more opportunities to manipulate the outcome, e.g. by misrepresenting the results of a local computation to a neighboring agent, or, more drastically, by simply not communicating with that neighboring agent at all, in an attempt to exclude him from the game. Our assumption of selfishness requires that we consider all forms of manipulative behavior when designing the economic mechanism. In particular, this means that we must provide incentives that ensure selfish agents find it in their best interest to perform the distributed computation correctly. While this chapter discusses the use of incentives to prevent these other forms of manipulation, one can also use cryptographic protocols to replace trusted parties in mechanism computation. This active area of study is covered in Chapter 8 of this volume. In the next section of this chapter, we briefly discuss two examples of DMD. Our third section is devoted to an in-depth exploration of the incentive issues in inter-domain routing. We conclude with open questions and exercises.